In this video, we're going to do some practice problems dealing with implicit differentiation and implicit functions. So first, let's start with the curve x cubed minus y squared equals 0. This curve is graphed here. And note that this is not a function, as it does not pass the vertical line test. It hits that function twice, therefore this is not, or the curve twice, therefore it's not a function. However, we can still think about the tangent line at any point here. We could do it for any point except for at 0, 0, and that's because it's not differentiable at that point. So here we're going to look at the derivative at 1, 1. And we're going to think about the slope of the tangent line at 1, 1. And note that that is trying to find the derivative at 1, 1. So we are going to do this implicitly. So the process is going to be, we take our curve, x cubed minus y squared equals 0, and we are going to take the derivative with respect to x of both sides. The right-hand side is really easy to do. That's just going to be 0. And the left-hand side has a straightforward derivative and one that is kind of new. So x cubed here, the derivative is just 3x squared. There's nothing weird going on. And then for y squared, that is our new kind of implicit differentiation. So one more time, this derivative, we have to do the chain rule. That's going to be the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. So this is going to be negative 2y times the derivative of y. So now what we're trying to do is we're trying to find dy dx. So we are going to solve for dy dx in this equation. And we can do that by subtracting 3x squared. So we're going to have negative 2y dy dx, which is the derivative that we're looking for, is going to be equal to negative 3x squared. Then we will divide by negative 2y. We will get negative 3x squared over negative 2y, or 3x squared over 2y, keeping everything positive. So that's the derivative at any xy point. And note that we can find the slope of the tangent line, the derivative at 1, 1, just by plugging in x equals 1 and y equals 1 into this equation. That's going to be 3, 1 squared over 2 times 1, 3 halves. And that is the answer to the question. So we could have done this for any xy point on that curve. Note that if we tried to do it at 0, 0, that wouldn't have worked because we'd have to divide by 0. So there is an issue there. All right, let's get some more practice with implicit differentiation. Next, we're going to find dy dx, find the derivative of this curve, x squared of y plus y equals 5. And note that this is our first example where we are not able to solve for y in this expression. It's not even that it's difficult to do, it's that we can't do it, or at least I have no idea how we could do this in this problem. All right, so we cannot do derivatives the old way for this kind of curve. We'd have to do it implicitly. So let's give it a whirl. We're going to start with our curve, and we are going to take the derivative of both sides with respect to x. So let's think about each of these derivatives individually. We have the derivative of x square root of y. The derivative of x is just 1. That's an easy derivative to do. And then we have the derivative of y. Equals 0. The derivative of 5 is just 0. All right, so to deal with x square root of y, we have to use the product rule here. And that's because we have x times square root of y. This is like f of x times another function, g of x, as y is a function of x. So with the product rule, we're going to have to do the derivative of the first times the second plus the first times the derivative of the second. Then we have plus 1, and then if we want to do ddx of y, this is actually really easy to do because we just have to rewrite it as dy dx, as that is what dy dx is standing for, the derivative of y. So now let's take care of these last two derivatives. We have the derivative of x is just 1. So we're going to write this as square root of y plus x. And the derivative of the square root of y we'll do off to the side here as we get used to it. We have to use the chain rule. We have our inside function is y, and our outside function is root x, or x to the 1/2 power. So we take the derivative of the outside, 1/2 something to the negative 1/2 power, leave the inside alone, and then multiply by the derivative of the inside, dy dx. So that's going to give us 1/2 y to the negative 1/2 times dy dx plus 1 plus dy dx equals 0. And just so we know what I'm doing, I replaced the derivative of the square root of y with our work that we did over here. All those are the same thing. All right, so now we need to solve for dy dx in this equation. And to do this, we're going to do this algebraic trick that we're going to do all the time, and this works for many other things past this. We want to bring everything without dy dx to one side and everything with dy dx to the other. So we are going to move everything without dy dx. So these are without dy dx, and we're going to move those to the other side. So I'm going to subtract root y, subtract 1, and do that to the other side as well. Now I'm going to be left with a 1/2 x, y to the negative 1/2, dy dx, plus dy dx equals negative root y minus 1. And the reason this works is now I can factor out a dy dx out of both terms here. Note when you factor it out of just itself, you're left with a 1. And now if I want to solve for dy dx, I can just do one last thing here, and that is divide by that whole term. So I'm going to get dy dx equals negative root y minus 1 divided by everything that was multiplied by dy dx. And there is my derivative, written in terms of x, both x and y. So this algebraic process in the last few steps is going to be done in almost every single problem. And again, the process is going to be move everything without a dy dx factor to one side and everything with it on the other. Factor out the common dy dx factor and then divide by what's left over. So we can solve for dy dx in that capacity. All right, let's do another problem. Here we're going to find the equation of the tangent line to the curve natural log of xy equals 2x at the point 1e squared. So before we get into the tangent line thing, what we really need to do is to find dy dx at the point 1e squared. So let's start with finding dy dx. We're going to start with our curve. And we are going to take the derivative of both sides. So on the left-hand side, we need to use the chain rule. We have the inside function is xy. The outside function is natural log of something. So this derivative is going to be 1 over the something. We're going to leave the inside alone. That's the derivative of natural log multiplied by the derivative of the inside. And all that is going to be equal to the derivative of 2x, which is 2. So now what I need to do is to take this derivative, x times y, which is going to need the product rule. So we're going to have 1 over xy, a remnant from the last derivative. And then we're going to have the derivative of the first times the second plus the first times the derivative of the second, all equals 2. Now we take these derivatives, and we're going to have 1 over xy. The derivative of x is just 1, so that's going to be y plus x, and then the derivative of y is our special thing we're looking for, dy dx equals 2. So now I need to solve for dy dx. And I think the best way to do this is to first multiply by xy on both sides. This will give us y plus x dy dx equals 2xy. We will subtract y, move up here. That's going to give us x dy dx equals 2xy minus y, and then we'll divide by x. And that will give us the derivative is equal to 2xy minus y over x. All right, so that is the difficult part of this problem. Now we just need to clean it up. Note that we need to find the derivative at 1e squared. So the derivative at x equals 1 and y equals e squared is going to be 2 times 1 times e squared minus e squared all over 1. And that's 2e squared minus e squared. That's going to be all together e squared. So remember, in our tangent line now, we have our equation is y equals f of a plus f prime of a times x minus a. Note that this is our x value. That is x equals 1. We have our y value here. That's y equals e squared. And we have our slope that we found before. That's just e squared. So the equation of our tangent line is y equals e squared plus e squared x minus 1. All right, and let's do one more example. We're going to change the notation up a little bit. Now we're going to find y prime if arctangent of x squared y equals xy squared. So note, first of all, that y prime is the same thing as dy dx. It's just a different notation that we're going to use there. And we'll kind of see it done with this notation, and you can decide which one you like better. Some people like the y prime thing. I think the ddx makes it easier to understand what you're trying to do. So here we're going to start with our curve. And to keep with this prime notation, we are going to take the derivative of both sides. So note that we're going to need the chain rule on the left, and we're going to need the product rule on the right. For the chain rule, we have that the inside function is x squared y, and the outside function is arctangent of something. And remember that the derivative of arctangent is 1 over 1 plus x squared. So seeing that in action, that's going to be 1 over 1 plus something squared. That's the derivative of the outside. Leave the inside alone, x squared y. And then we are going to multiply by the derivative of the inside function, x squared y prime. And this is going to equal, using the product rule, x y squared prime. That's going to be the derivative of x times y squared plus x times the derivative of y squared. All right, now we need to use the product rule again for the x squared y, and we will write this as 1 over 1 plus x squared y squared times the derivative of x squared times y plus x squared times the derivative of y, and that is y prime. And this is all going to equal, on the right-hand side, the derivative of x, which is 1. That's just going to be y squared, plus x, and then the derivative of y squared, we need to use the chain rule, and that will give us a 2y y prime. So lastly, we have the derivative of x squared is going to be 2xy plus x squared y prime equals y squared plus x2y y prime. And we need to solve for y prime. So before we do that, I just want to make clear that this is a different notation that we could use, but there's a couple of downsides to this notation. One is the prime doesn't tell us what variable we're taking the derivative with respect to. And we're kind of seeing that we have a couple of variables floating around. It actually does matter in some cases how that's going to work. We're going to do implicit differentiation later in section 4.6 or 4.7, related rates. And we are not going to be able to use the prime notation because it's going to matter what variable we're taking the derivative with respect to. So I would urge you to use the Dydx notation, but know that this is available to you. All right, to solve for y prime, the first thing we're going to have to do is to get rid of the fraction. We're going to have to multiply by 1 plus x squared y squared on both sides. So that's going to give us 2xy plus x squared y prime equals a y squared times 1 plus x squared y squared plus x2y y prime times 1 plus x squared y squared. So now we're going to bring everything with y prime to the other side. So we can write that as 2x, and everything else without the other side. So we're going to move the 2xy to the right. We're going to move everything with the y prime to the left. We can write that as negative x 2y y prime times 1 plus x squared y squared plus x squared y prime is going to equal y squared 1 plus x squared y squared minus 2xy. And then I can factor out the y prime, which is what we're trying to do, and we're left with this big nasty thing, minus x2y 1 plus x squared y squared plus x squared equals everything on the right-hand side. Then we have one more step, and that is to divide, and we'll do that up here. And we can write this as y prime equals y squared 1 plus x squared y squared minus 2xy all over negative x2y 1 plus x squared y squared plus x squared. That is a gross example of implicit differentiation. We had to do product rule twice, we had to use chain rule twice, and there was a lot to kind of take past that. I want to urge you one last time not to use this prime notation. We had to write less things down, but really all we saved ourselves from doing is just writing Dydx a few times. But it's going to be easier to do this Dydx as we kind of go forward. And note that what we just did here is a pretty complicated problem.